Inside a Beijing laboratory, a team of physicists built an experimental refrigerator with no compressor, no refrigerant gas, and very few moving parts. The device uses a changing magnetic field to move heat through carefully arranged solid materials. If this works at scale, the machine sitting in your kitchen right now, the one that hums, leaks a little bit of a greenhouse gas over its lifetime, and eventually breaks down, could become as outdated as the icebox. Understanding its potential begins with how magnetism can change a material's temperature, and why researchers see solid-state cooling as a possible long-term shift in appliances. Many cooling machines used in daily life are based on the same underlying process. Your refrigerator, your air conditioner, the one in your car, the one keeping vaccines cold at the pharmacy, the one behind the walk-in freezer at the grocery store. All of them run on the same idea, invented in the 1800s. Compress a gas, let it expand, and use that expansion to pull heat out of a space. It is called vapor compression refrigeration. And according to industry research from the Rocky Mountain Institute, it has dominated the cooling market for nearly a century, largely unchanged in principle. It is one of the most quietly important inventions in modern life. Without it, we lose food safety, medicine storage, and livable indoor temperatures in hot climates. Despite its importance, the mechanism usually remains invisible to the people who depend on it. Inside the kitchen, several costs of conventional cooling remain largely unnoticed. To make cold air, that little compressor is running constantly, using electricity and wearing down moving parts. That is part of why fridges eventually fail, and it depends on a refrigerant gas sealed inside the system. Some of those refrigerants are potent greenhouse gases. According to the Rocky Mountain Institute, R134, one of the most common refrigerants used today, has a global warming potential about 1,430 times that of carbon dioxide. Multiply that across every fridge, every AC unit, every freezer on the planet, and you start to understand why researchers have spent decades trying to replace the compressor entirely. The physical effect behind the alternative has been known for well over a century. Scientists have known since 1881 that certain materials heat up when you apply a magnetic field to them and cool down when you remove it. It is called the magnetocaloric effect. In 1976, physicist G.V. Brown built the first room temperature magnetic refrigerator using gadolinium, a rare earth metal. It worked, but for decades, these machines stayed stuck at the prototype stage. The reason? To carry heat away from the magnetic material, most designs used a fluid, usually water, flowing around it. That fluid became the bottleneck. It slowed the whole cycle down and wasted a lot of the cooling effect. So, a team at the Institute of Physics, part of the Chinese Academy of Sciences in Beijing, asked a different question. What if, instead of using a liquid to carry the heat away, the heat moved directly, solid to solid, with no fluid at all? A simple comparison helps explain the underlying temperature change. Picture a rubber band. Stretch it fast and hold it against your lip. It feels slightly warm. Let it snap back, and it feels cool. The changing shape produces a small but noticeable thermal effect. Certain metal alloys do something similar, but with a magnetic field instead of a stretch. Apply magnetic field, and the material heats up. Remove the field, and it cools down reliably over and over. In older magnetic refrigerator designs, engineers ran water past that material to carry the heat somewhere useful. But moving fluid limits how quickly the cycle can repeat and introduces additional losses. In a paper published in the journal The Innovation in May 24, the Chinese Academy of Sciences team, led by researchers including Yuan Lin, Jing Wang, and Baojin Shen, described building something they call a hybrid magnetic regenerator. Instead of fluid, they layered the magnetic material directly against a different solid material that conducts heat extremely well, packed so tightly together that heat can move from one to the other with no middleman. According to the study, this fully solid-state design removed the frequency limit that fluid-based systems were stuck at. In practical terms, the fully solid design is intended to cycle faster and transfer more heat within the same period, closing the gap between interesting lab idea and something that could actually compete with your kitchen fridge. The same heat transfer method may have applications beyond a household refrigerator. The research also points toward more targeted forms of thermal management because the design needs no pipes, no fluid, and no seals that can leak. It is just solid material touching solid material, the same. Research group has since shown, in a newer paper published in the journal PNAS, that this solid-to-solid heat transfer can be aimed at very specific points, almost like a heat scalpel, that matters far beyond your kitchen, modern electronics, the chip in your phone, the battery pack in an electric vehicle, the servers inside a data center, all generate heat in tight, specific spots. Cooling those spots efficiently, without bulky compressors or refrigerant lines that can leak, is a growing engineering headache as devices get smaller and more powerful. A solid-state system that can be shaped and placed exactly where the heat is generated could end up mattering just as much for electronics and battery cooling as it does for the appliance in your kitchen. What started as a better way to build a fridge is turning into a general-purpose tool for managing heat. For consumers, quieter operation and the absence of refrigerant gas would still have to compete with purchase price, proven efficiency, capacity, reliability, and repair options. The present stage of development must be separated from the longer-term possibility. What the Chinese Academy of Sciences team built is a laboratory prototype, described in the paper itself as a conceptual device. It isn't sitting on a shelf at an appliance store, and there is no announced timeline for one. Magnetic refrigeration, as a category, still has real hurdles ahead of it. The magnetic materials involved, like gadolinium alloys, are more expensive than the gases used in ordinary fridges, and building the strong compact magnets adds cost. Across the broader, solid-state cooling field, researchers and journalists covering the space have noted that current systems often still cost more, and in many cases run less efficiently than a standard compressor. The remaining engineering barrier has not disappeared, although this design may move it further toward a practical system. This research is a genuine step forward on the specific engineering bottleneck that held magnetic refrigeration back for decades. It is not yet a finished product you can buy. The contrast between mature compressor technology and early solid-state research is striking. The fridge humming in your kitchen right now runs on essentially the same core idea as one built in the 1800s. And yet, a few labs, quietly, working with magnets and metal alloys might be building the thing that finally replaces it. Not with something flashy, but with something quieter, simpler, and if the engineering holds up, kinder to the planet. Technology like this rarely arrives all at once. It arrives in small, unglamorous steps, in papers most of us never read, years before it shows up in a store. The broader question is which other familiar machines may eventually be redesigned through quieter advances in materials, thermal control, and solid-state engineering. A commercial refrigerator would also need to cool a large insulated compartment continuously, recover after the door opens, operate quietly for years, and meet safety standards at a competitive cost. Those practical demands are much harder than demonstrating a small temperature change in a controlled laboratory device.